Hi class. In this video here we want to move into section 2.5, and this is talking about maximum and min problems. This might also be referred to as optimization problems. If you were to take like a Calculus 1 class, a traditional Calculus 1 class, this would be considered optimization problems. So we want to optimize something. And to do that, we're going to use what we know about maximum and minimum values, and we're going to do some business and economics application problems. So I have this video here is going to be just basically 3 examples of this procedure, this process. And the first 2 examples are going to be kind of like maximizing area and volume, and then the last problem I get to will be a business and economics problem. Okay, so here's going to be a strategy we're going to use for solving maximum min problems. First thing you're going to do is you're going to read the problem very, very carefully. You have to understand what you're given and what you're being asked to find. And if relevant, you're going to need to make a drawing. So in the first 2 problems we do, I'll do a drawing to help us figure it out. Next, you're going to make a list of appropriate variables and constants, noting what varies, what stays fixed, and what units are used. Okay, you're going to label the measurements on your drawing if one exists, if you need it. So again, this is just like reading it carefully and then just writing down every single thing you're given. Okay, the more information you can glean from the initial problem, the easier it'll be. Okay, then what you're going to do is you're going to translate the problem to an equation involving a quantity Q. Okay, this quantity is what you're trying to figure out to find the maximum or the minimum of. Okay, so what you're going to want to do is you're going to try to represent Q in terms of the variables that you found in step 2. Okay, I'm going to do a problem that involves 2 variables, you'll see. And then I'll write it as an expression of 1 variable. So you really just want to get it in terms of 1 variable if possible. Next, you're going to try to express Q as a function of 1 variable, as I said, and you're going to use the procedures developed in all the sections before to determine the maximum and min values and the points at which they occur. And I wish I could say that this stuff was just, these problems were like, oh, just follow this formula and you'll be able to get it. It's not 100% like that. So it's everyone's favorite type of problem in mathematics. It's word problems. So they can be a little tricky, and I hate to say it, but practice makes perfect. All right. So here would be the first example that we're going to do. Okay. We're going to need to enclose a rectangular field with a fence. Okay. And what you do is you have 500 feet of fencing material, and a building is on one side of the field. So you don't need any fencing on that side. Okay. Determine what dimensions of the field, okay, that will enclose the largest area. Okay, so here's what you want. You want the largest area. Okay, you see largest area. Okay, so what that means, to put it in terms of calculus, is we want to maximize some area. Okay, maximize an area. Okay, so that tells you, that's going to be the calculus part. All right, so we have this field, okay, and on one side of the field is a building. So in this case, a drawing is going to help me here. Okay, so we have this field, and we have this building on one side of the field. Okay, and what we want to do is we want to put a fence around the field like this. Okay, so this is the area we want to maximize. Okay, we want to maximize this area. So to do that, which, like, for example, why, people might be like, well, if you got 500 feet, like, why don't you just do, half a foot here, half a foot here, and then 499 feet this way. It's just like there's a bazillion different dimensions you can pick from, but there's one dimension, okay, for the length and width of this rectangle here that maximizes the area. Okay. All right, so to do this then, okay, what you're going to need to do is you're going to need to figure out, some equations here. So you're going to maximize an area. So you want to maximize an area. Well, what is an area formula, right? An area of a rectangle, because again, it's told it's a rectangular field, is equal to length times width. Okay, So look, I'm going to label the length variable as x, all right, and the width variable as y. Okay, so it looks like here that the area formula here is just equal to x times y. All right, but look, here's the problem. There's two variables here, right? And so, you know, this is calculus of a single variable. Okay, so what we're going to need is we're going to need some type of constraining variable. All right, or some other second variable. And the key for this is that you have 500 feet of fencing. Okay, so your 500 feet of fencing will be equal to, well, look, you have 2 y's and 1 x. So the width, the 2 widths plus the 1 length need to sum up to 500 feet because you're going to use all the 500 feet. Well, look, now I can solve this for a single variable, right? So what I can do here is I'm going to solve it in terms of x. So x is equal to 500 minus 2y. Okay, and what you can already see here, just real important, like y can't be more than 250 feet, right? So we already know that, okay? Because if you plug in like, you know, something larger than that, you're going to get a negative number, and also you wouldn't have enough fence. So then our area formula then becomes, I'm going to replace the x with this. So our area becomes a function of a single variable y. Okay, you can change these x and y's if you want. It doesn't really matter. And I'm going to distribute, so this is 500y minus 2y squared. Okay, so now I want to maximize this function. All right, so I'm going to go to the next slide to do this. So I want to maximize this function. So our area function was a function of the y variable, and it was 500y minus 2y squared. So let's take the derivative because we want to maximize it. Okay, so take the first derivative. So a prime, the first derivative here, okay, this becomes 500 minus 4y. Okay, so we want to maximize this. So you want to find a critical point for this. So to do that, to find the critical value, right, because maximum, minimum values occur at extrema occur at critical values, right, you're going to solve where the first derivative is equal to 0. Okay? So now you're going to solve 500 minus 4y is equal to 0. You're going to add the 4 over, so you get 4y is equal to 500. You're going to divide both sides by 4, and you get y is equal to 125. All right, so now here's the thing. You found a critical value, but you don't know if you have a max or min value. All right, you just know that that's a critical value. So you can use the second derivative to determine if the value you found is a max or min. So if you just take the second derivative here, right? So you can see that the second derivative here is just equal to negative 4. So if you were to plug this into the second derivative, you do just get negative 4, which is less than 0. So when the value plugged into the second derivative is less than 0, we know we have a maximum value. That's great. Okay, so then what you can then just say here is, thus, the dimensions that maximize the area are, well, look, we see y is equal to 125 feet. And did we had a formula for x? Like if you look back, if we know y, we can actually solve for x, because look, x is equal to 500 minus 2y. So it's 500 minus 250. So this is 250 feet. So looking at just our building here, going back, we don't need the building, right? So the length here will be 250 feet. And each of the widths will be 125 feet. And if you look, you see that that adds up. 125 plus 125 plus 250 adds up to that 500 feet. So you're using all the fencing, okay? And you're maximizing the area. So there's no other dimensions you could pick. Literally no other dimensions you could pick that would maximize the area here. So this is good. So look, what we did here was we figured out, a formula we were trying to maximize. If it had two variables, we had to have some other second variable or constraint that helped us plug in to get it in terms of a single variable. All right, let's do another one. Another construction type problem. Okay, so from a thin piece of cardboard, 8 inches by 8 inches, okay, square corners are cut out so that the sides can be folded to make a box, okay? So the question then is this: what dimensions will yield a box of maximum volume? Okay, so two questions here. What dimensions will give maximum volume? Okay, and then what is the maximum volume? Okay, so here, right off the bat, what we're trying to do is we're trying to maximize volume. All right, well, look here. So the first thing you have to do, and this is where it gets a little hard, is you have to find the picture for this. Okay, so you're going to start by drawing this cardboard that's a square cardboard because it's 8 inches by 8 inches. Okay, and then what you're going to do is you're going to cut square corners. And we don't know the length of these square corners. Okay, but every corner is going to be the same. And look, you can see if we're going to cut a square corner, the sides of the square have to be the same, right? And we're going to do that in every single corner. And then what you're going to do is you're going to take away these pieces. You're just going to, you're literally throwing these pieces away after you cut them. And then you're folding the sides up to get this this cardboard box here, okay? And you can see here that the length of the cardboard box, well, it's 8 inches, but then you're subtracting x on each side, so you're subtracting 2x, and it's the same on the width, okay? So the volume, here, this volume, we know the formula for the volume. It's length times width times height. So volume, turns out we can write it in as an equation of just a single variable x. Well, the length here is 8 minus 2x. The width is also 8 minus 2x. And look at the height. Because we're folding these flaps in, the height of this box is x. All right, just so we're clear here, the domain of this, all right, you can never have a negative length, right? So the domain of this the value of x has to be somewhere between 0 and 4 open brackets, okay? Because you can't have a height of 0, so it has to be at least greater than 0. And you can't be greater than 4, right? Because if you plug a value greater than 4 in here, or even 4 itself, 4 would get the length and width would be 0 inches. Then you can't be more than 4 inches for x, because then you'd have a negative length and width, which you can't have. All right, so let's just distribute here, right? So distribute this out. You get 64, because 8 times 8, right? Minus 16x minus 16x minus 32x plus 4x squared, all times x. So then when you redistribute this, I'm just going to write it with the highest degree first. You get 4x cubed minus 32x squared plus 64. Okay, and that's the volume function. Okay, so I want to maximize this volume. Okay, so generally I tend to think this is like the hardest part, right? Like once you figure out the function you want to maximize, then it's just calculus from here. Right, so to maximize this, we're going to take the first derivative. So let me rewrite the volume function. So the volume is a function of this x, okay? And it's equal to 4x cubed minus 32x squared plus 64. All right, so it's a little bit of algebra here. The derivative here, okay? So you bring this 3 down, right? So you get 12x squared minus 64x, and then this, the derivative of this 64 is, and I'm sorry, I forgot, forgive me, I made a little bit of a mistake here. Distribute the x, this should be 64x. Sorry, my apologies. I forgot to distribute that x there. Plus 64. Okay. So from here, what you're going to next do is you're going to factor out a 4. I think you can factor out, yeah. When you factor out a 4, you get 4 times, you get 3x squared minus 16x plus 16. Okay. Now what you want to do is you want to find the critical values of this function. Okay, so to do that, you're just going to solve it by setting it equal to 0. So you're going to divide both sides by 4. Okay, that goes away. So you're just left with 3x squared minus 16x plus 16 is equal to 0. And you can do this on your own, but this is just a very simple trinomial that'll factor into 3x minus 4 times x minus 4 is equal to 0. So you have two solutions, right? You set this equal to 0, you get x is equal to 4/3. You set this equal to 0, you get x is equal to 4. But look, the thing that's tricky here is you have to go back and look at your domain, right? Like you can't have a value that's 4 or greater because the value of x has to be between 0 and 4. So this critical value we reject. All right, so this is the critical value we're interested in. All right, but again, we don't know if we have a max or min. So you're going to use the second derivative. So if you take the second derivative here, bring the 2 down, you get 24x minus 64. What you're going to do is you're going to take this and plug it in. All right, so that's 8 times 4 is 32, minus 64. So this is minus 32, which is less than 0, which is great, okay, because that means we found a max. So thus a value of x is equal to 4/3 inches produces the max value. Okay. So let's just, we've got the dimensions now, okay? You can plug in 4/3 here and get the length and width, but let's just find now what is the max volume. Well, to figure that out, use the volume function. So volume of x, going back, our volume function, it looked like it was 4x cubed minus 32x squared plus 64 x. So what you're going to do is you're going to plug in this value, right? So you're going to get 4 times 4/3 cubed minus 32 times 4/3 squared plus 64 times 4/3. And not to waste time, but if you plug this in, you'll end up getting 37 and 25 27 inches cubed. And that's the maximum volume here. All right, I'm going to break this video up now into a second part. So when you come back, I'll do another video just to keep these videos on the little bit shorter side. I'll come back and I'll do an economics example here.